Okay. Welcome to another seminar, everybody. Today we have Martin Wosnik presenting, who most of you probably know, but for those of you who don't, he's an associate professor here at UNH, and also the co-founder and director of UNH's Center for Ocean Renewable Energy. He'll be presenting on tidal energy research.
Thank you. So good afternoon. As I was putting together this presentation, I was trying to both give you an overview and then also go into depth on some parts so you get more of the things we're really working on. It remains to be shown how much I succeeded in that. At some point I may have to actually kind of gloss over some things and move on, but I think overall my intent is to give you a good idea of the range of tidal energy research we have been doing over the past few years. So,
sorry, Martin, just click on the slide.
So here's what I'll go through. I'll briefly talk about the overall tidal energy resource that we have in the US. I'll talk about the scale-up process in ocean renewable energy development. Then I'll get into cross-flow turbines a bit more, talk about some tow tank experiments we've done right outside here, some modeling, and then get into mostly picture show and some data from our open water deployments. We have a couple of those. All right, so here's the opening slide. Lots of big numbers. It's quite a bit to absorb, what to pay attention to. I mean, either the red numbers or the black numbers, either power or energy. So in the US, we have about 1,100 gigawatts installed electric generating capacity. On average, we use about 470 gigawatts average throughout the year. Here are the numbers that you can get from tidal, ocean current, wave energy, and a couple of estimates, sort of a low bound and a high bound from wind. Okay, so that's a complicated slide. I gave a presentation at Ocean Discovery Day. This is much better, I think. Shows a very big sun. So wind energy is once recycled solar energy. Wave energy is twice recycled solar energy, and then tidal energy is 2/3 lunar and 1/3 solar energy. So tidal energy is actually a fairly small part of our, or could be at best a very small part of our electric energy portfolio. Most of the resource is located in Alaska, actually, so that's not good either. But we have well, for us at least. But we have some niche applications where this might work quite well. Certain estuaries, inlets, and bridges, those kind of. We'll explore those a bit more later. So keep this in mind. That's really a massive part of the answer. That's a smaller part of the answer, wave energy, and that's very hard to do. We're still struggling with that. Tidal energy is a bit more, easy to do, a bit more obvious how it can be done, but it could at most be a very small part of the solution. So in ocean renewable energy R&D, you work with theory, experiments, simulations, and then you go through what we call a scale-up process. You start small, inexpensive, and then you grow it, right? And you hope that before you move to the next technology readiness level or the next stage, that your answers from theory, models, and experiments somewhat agree, or that you understand why they don't agree before you spend more money on this. And at some point, you have to go into open water. Still a scale deployment typically. The first time you go into open water, you're still working at maybe a 1/10 to 1/3 scale or something like that. But that's sort of how you work through this in order to not just waste money. So the focus of this presentation is on tidal energy and specifically on in-stream hydrokinetic energy conversion, also referred to as marine hydrokinetic energy conversion, MHK. And here we're kind of doing two things. We're looking at single turbines. We're interested mostly in performance. And we're looking at sort of ahead at array deployment. We're looking at wakes and how these wakes decay and how they possibly interact and those kind of things. So performance, wakes, those are the two focus points of this study. Range of scales. So we work from the blade scale, meaning we literally take little blade sections and evaluate like lift, drag, cavitation characteristics, in a small cavitation tunnel. Then we go in the tow tank, that's about a quarter of a meter or so, scale of a meter. And then we go into open water where we can work from, say, 1 meter to 4 meter. It's pretty crazy as a university to actually get into this like 3-4 meter scale already. That's very large. Full scale, say a full scale 1 megawatt unit might be as big as 16 to 20 meters, depending on the resource. All right, what is a cross-flow turbine? This is how they started with these various devices, various turbines. And maybe I'll stand over here so I can use the pointer without being in the way. These were actually quite a bit ahead of their time. This turbine here is on the northern end of the Gaspé Peninsula. It's 110 meters tall. It was built in 1988 or so, 87, 88. It was rated at 4 megawatts at the time. They had to downrate it. This is when horizontal axis wind turbines were playing in the 500 kilowatt range. Okay, so these were much bigger at the time. They had to downrate the device because they didn't quite understand the unsteady loading that well. There were fatigue issues, and after 5 years it was shut down entirely. It's still standing, sort of a monument to the early successes and failures of these turbines. There were fatigue issues. They were typically exaggerated with the power ratings. Actually, California made a mistake back in the early days of wind to actually pay developers based on rated capacity, not on energy delivered. So everybody was overrating their devices. And turbines had very low capacity factors. So there's renewed interest in the marine environment, both for MHK applications and floating offshore wind, and then some other applications in terms of densely spaced arrays and urban wind. Cross-flow devices are quite promising in dense arrays because their wakes decay very quickly, and people don't really know why that is. And they're also simpler machinery. They're more complicated from a fluids perspective because they're unsteady devices. We'll talk about this in a moment. But they rotate in the same direction no matter where the flow is coming from, as long as that flow is approximately perpendicular to the axis of rotation. Right? So you don't have to you don't have to change things around. You put the thing in, it just runs. Okay. And for offshore wind, you could possibly put the power train at the base of the device, which would actually make for much less. You would have much less of a need for balancing ballast below compared to having a heavy power train on top of the nacelle. All right, so we have to have a little vector diagram. This is a simple diagram of a single-bladed cross-flow turbine. Axis right here, blue is the incoming velocity, orange is, black is the rotational velocity of the blade, and then the resulting vector is in red. So if you actually animate this as the thing rotates around, so the flow is always from the top now, okay? And then you have these two vectors popping up, green and red. This is lift and drag, and those produce torque. So you can see that you have very short bursts of very high torque coefficients. Then it doesn't do much for the rest of the rotation. So it's an unsteady device. But if you have multiple of these blades, you could potentially smooth out this torque curve quite a bit. Make this thing work reasonably well. That's the idea behind it. Okay. All right, so here's a 2D RAND simulation of this. RAND is Reynolds, Average, Navier-Stokes with essentially a two-equation eddy viscosity turbulence model and flows from left to right. And you can see that, so this up here is where it produces most of the torque at really shallow angles of attack. And then right here where this red thing sort of pops up. That's where you encounter dynamic stall, which is a process where you have a leading edge vortex forming. While that forms, you have really high lift, and then when it sheds, you have a sudden drop in lift and drop in torque coefficient. And so it's not unlike having cavitation, having sheet cloud cavitation on a hydrofoil on the top. You go through rather high angles of attack. All right, and this is another picture that shows that the higher the speed of rotation, this is the rate of non-dimensional rate of rotation, also called tip speed ratio. And the faster it rotates, the more shallow the range of angles of attack gets. So the less separation you have. So the less, and that's all related to how solid these devices are. So the faster they can rotate, the less you encounter these things. But anyway, you're dealing with unsteady hydro or aerodynamics. And there are a lot of similarities to rotorcraft flows. So some of the codes that we use actually come from the rotorcraft industry. We have blades moving into the flow, blades moving out of the flow. That sort of thing. Okay. All right. So what do we have in terms of engineering tools? Well, we can do experiments. If you go to large scale, experiments get very expensive. So you don't want to play with large arrays and try to build like 10, 15 models at a large scale. We want to do this numerically. So for numerical tools, we have a number of sort of a range of models with increasing fidelity that can models. We have very simple momentum or vortex line models, panel methods, then full Navier-Stokes simulations, either Reynolds averaged Navier-Stokes or large eddy simulations. And then the actual line model is sort of a method where you can actually reduce required resolution, but still embed this into a full Navier-Stokes simulation. And there's been a real difficulty predicting performance in a cost-effective way of these devices because they're unsteady. People have been struggling with this. And the clear trade-off here is computational cost versus accuracy. We'll talk about the cost in a moment and how much time it actually takes to simulate these, and then how we can reduce them. All right, so, well, we want to understand performance better, improve performance modeling, and also understand wake recovery so we can put these in arrays. So what we've done here is we've done experiments in the lab using the tow tank. You may have seen that turbine test bed standing on the side as you walk through the lab. It's the funny hydrofoil frame with the black three-bladed turbine in it. And then we did some CFD to look at different classes of models. We did some blade resolved simulations and then developed this actual line model compared to the blade resolved simulations. That's the turbine test bed out in the tow tank. This turbine has a diameter of about 1.1 meters. Typically, we work with about a meter scale turbine. I'll show you why in a moment. And the test bed, you can see that it rides on these rails. There's a servo motor driving it. And if you look at a schematic of it, we can measure torque in the line right here. We have another redundant torque measurement up here with a slowing arm and a load cell that's not shown here. The servo motor drives it, so we can prescribe tip speed ratio and step through a power curve. And then we have load cells on this whole frame to get overall thrust on the system. And we can tow it without a turbine to get a tear thrust and then subtract that to get turbine thrust. Right? And we can also do wake measurements with the Victrino probe here. We can tow the separate carriage behind the main carriage. And here's a 4-prong lab version of a Victrino that can measure 3 components of velocity at 200 hertz. Okay. To get good signal to noise, we have to actually see the towing tank with hollow glass spheres, which tend to clog up the filters. So, anyway. All right. PhD student that was here until a couple of years ago, Pete Beauchamp, actually, he renovated the whole tow mechanism and this whole test bed, and he automated everything. Prior to this, we could do maybe tens of tows, and then we could literally do thousands of tows. Some of you may recall seeing Pete sitting. It took him like a year to prepare an experiment, to get everything automated, but then he would just sit there for like 3 weeks, just do nothing. Just watch the thing go back and forth, and watch his plots pre-populate, his pre-made plots populate automatically, which is kind of a beauty to see. So that's a typical towing profile. You can see the turbine RPM, torque, drag on both load cells, and then the different velocity measurements. That should play, yeah. So we actually spin the turbine. The tank is really short. If I could change one thing about the tow tank, I would blow out the back of the building and make it like 5 times longer. But that's probably not going to happen. So we get about, depending on the tow speed and tip speed ratio, we get about 10 to 20 steady state or quasi-steady state rotations over which we average. And we do this over and over again. We wait a few minutes between each tow for the tank to settle down, and so forth. So we want to talk about only 2 turbines. We tested a number of them, but these are the two we have most of the data for. It's what we call the UNH reference vertical axis turbine. It's a high solidity turbine, which we built from these NACA 0020 hydrofoils that we had. They're pretty, not cheap to make. We had a whole bunch given to us by a company who went out of business with doing this kind of work. So I'm quite happy to have lots of these laying around. It's a meter by meter. It's a reference model. Here's what these typical power and thrust curves look like. This is a power curve, non-dimensional power versus non-dimensional rate of rotation. Right? So power coefficient versus tip speed ratio. And you basically measure the mechanical power of the power on the shaft, and then divide by the power available in the flow that you intercept. Okay? That's how you calculate this. Same thing for the drag or thrust coefficient. So you can see that the drag and thrust goes up monotonically. So if the turbine rotates really fast, it looks almost like a solid object to the flow. But there's a clear peak in power, right? So this is your peak tip speed ratio of about 1.9, 1.8, 1.9. But this turbine operates best. It's 0.25 or 0.26 is fairly low. This turbine was not designed for maximum power. It was designed to be a simple reference model. Big horizontal axis wind turbines may reach as high as 0.5. And we have another turbine, which I'll show in a moment, which also went a bit higher. We did some weight measurements. This is a full grid of 270 points or 270 toes. Look at the wake structures. And so this is what the wake looks like. Mean velocity deficit on top, turbulent kinetic energy on the bottom. So you can see where the kinetic energy is strongest. And you also see this strong mean advection coming down. And that really hadn't been seen before like that. And we actually then looked at, a couple of equations here. When we actually went through the governing equations term by term and tried to figure out which ones are the ones that drive this here, right? So both in the mean momentum equation, the vertical advection is the strongest. The viscous terms are so small you don't even see them. And in the turbulent kinetic energy equation, again, the advection of kinetic energy is the strongest aside from production. And dissipation is also really, really small. All right, moving on. Effects of Reynolds number. This is actually really important. So here we're running at different toe speeds, and you can see how this curve keeps creeping up, right? Whereas the thrust doesn't really change all that much. So if you plot this curve, which is power coefficient versus Reynolds number, you can see that down here, there's a really strong dependence on Reynolds number. And up here is where it levels out. So you should be doing your experiments from here to the right if you want to use your results to extrapolate at full scale. The problem is with laboratory facilities, most people don't have a tow tank like this. They have smaller flumes. So everybody in university labs is working down here. So they don't really see the forest for the trees if they do that. The error bars are quite high here because the torque sensor was sized to have the right resolution at the higher end of the torque range, not down here. All right. So that was an important insight, and that actually got us some work. In a moment, I'll explain what kind of work that got us some years later. Dominant timescales. So if you think back to the 2D visualization, you see that on one side you have these blades passing and flow not really separating. So you get, and that's over here on this part. So you see dominant timescales that are multiples of the blade passage frequency. You can clearly pick those up. Whereas over here, where you have the dynamic stall vortex coming down and really broadly mixing out, you just see this broadband turbulence in the spectrum. All right. We did another experiment for the Department of Energy. This is called the Reference Model 2 that was designed by NREL and Sandia, National Renewable Energy Laboratory, and Sandia National Labs. And I wrote a proposal for that like 4 years earlier. They have this dual rotor configuration, and I proposed it with just a single rotor because the dual would make it too small and you can't really figure anything out. They picked another lab to do the work with a dual rotor, actually, University of Minnesota, where previously worked for a couple of years. So it hurt to see the work go there. But then they couldn't really figure out what was going on. The models were so small that it also really matters how you mount the blades. They had the blade cord mounted by just a fraction off, which reduced performance. The dual rotor, the left one rotor had a 5% efficiency, the other one 8%. So like, what is going on? I'm like, well, it's Reynolds number effects, right? That's all it is. Here your Reynolds number effect. So it turns out for this turbine, they're actually much more pronounced. You can see that at the Reynolds number of 0.4, I think the Minnesota experiments were at an even lower Reynolds number. They were barely reaching 0.1. You don't get much performance out of this, right? So you have to again get to these higher Reynolds numbers that I showed before, this leveling off of the CP curve to get to the right kind of performance. And we're still seeing a bit of an increase here. You also may notice that we're missing the higher rotation speed data up here. Things were getting a bit hairy in the tow tank with this thing flying through and rotating, and it's a big complicated spring out there that were so exciting. And then full disclosure, we broke the tow tank about 7 or 8 years ago, which was why we had to rebuild it because of this turbine business. All right, we see something fairly similar for the near wake, but this is a turbine that operates at a much higher tip speed ratio, so we don't see the dynamic stall as much. So, all right, how am I doing for time here? Okay. So we tested, did a quick test. What was the effect of struts? So the struts for this turbine were also NACA 0021 profiles, and we made some struts that are really, really bad, which are just round pipes. So if you know your fluid dynamics, round pipes have a really high drag coefficient, much higher than streamlined foils. So here you can see the parasitic power coefficient, the negative power coefficient due to struts versus tip speed ratio. For the NACA 0021, we're losing, and this turbine peaked at about 3. So we're losing maybe 2 percentage points with these NACA struts. If we mount cylinders, we lose a lot more. So if you look at the power curves, we have the original power curve right here, and then we have an entirely negative power curve. So if you mount round struts, these blades don't provide enough thrust to turn the thing at all anymore. And that's so that was sort of silly, but it provided a good reference case. And since then, other labs have done studies with square, slightly rounded, and whatever struts, and use that same methodology to kind of sort out what works and what doesn't. Interestingly, the drag coefficient doesn't really change much. It actually is a bit less for the round struts, and that is probably related to not taking as much power, not taking any power out of the flow wheel. All right, good. We're going to talk about modeling real quick. Just a few slides. Blade resolving, CFD, and then neck chair line model, and I think I have one slide on this Sandia vortex wake model. And then, yeah, open issues. We never quite wrapped that up. So if you do a fully blade resolving simulation, you have to actually refine your grid more and more the closer you get to the blade. You have to basically refine your viscous lengths on the blade. Viscous length scale is defined in terms of it relates to what happens in the boundary layer. Okay, and the very near wall region out to viscous lengths of maybe 3 has a linear relationship between velocity and distance from the wall. Then it gets more complicated. So unless you get inside of a y plus of, and it's typically referred to, the viscous length has units of y plus, which is wall distance over viscous length, which is kinematic viscosity over friction velocity, which is a whole other thing I'm not going to get into. But you need to get really, really close to the wall within one viscous lens to really resolve that sublayer to get good results. So your grid requirements are very, very large. You need massive grids. And that then requires lots of computational time. So to simulate the UNH reference vertical axis turbine with typical 1 or 2 equation turbulence model, we tried both the Almaraz, which is the 1 equation model, and the K-omega SST. It requires on the order of 10,000 CPU hours for 10-second operating time. Okay, that's 1,000 CPU hours for 1 second operating. So that's not cheap if you do that. And so here's an overview of, it's a simple graph, but it shows quite a bit. We have 2D simulations, the 2 equation model, 1 equation model, and 3D simulations, K-omega SST and Almaraz, and then the experiments. So you can see that the 2D simulations greatly overpredict everything, which is to be expected because you have this added, I guess, blockage in 2D. And we're still off by about, I think, -10 or +15% in performance here. So it's okay, but not great. And over here is thrust, where they all do pretty well, actually. All right, so here's another way to approach this without having to fully resolve everything on the blade. This is called an actuator line model. It was developed actually for wind turbines by a Danish group. And what you do is you basically solve the Navier-Stokes equations, and you add a forcing term for the effect of blades. You don't resolve the blades, you put forcing terms in where you want the blade to be. And then it comes all about how to actually model this forcing term and how to smooth it out or spread it out and all those things, right? So you don't need to resolve the boundary layers. Meshing is very simple. And you can still implement this into high resolution simulations, okay? So ultimately, the goal of us was to actually implement this in a large eddy simulation, which is sort of the most high fidelity simulation, which is really a direct numerical simulation above some subgrid cutoff scale, and below which you model the effects of dissipation, right? So you get the large scales right, and you don't resolve the small scales, but you model the effects of the small scales. And the filter width is typically just the cube root of your mesh volume. Right? So an easy way to cut this off. So here's some. So these were our first results, actually. Remember how one data point took 10,000 CPU hours? Now we're able to do all of this entire curve in less than an hour. We're like, yay, this is great, it's working. But this, we hadn't really tweaked all the parameters yet in the most physical way. So we weren't quite done yet. Once we actually added all of these various effects that should be in there, some end effects model, a proper improved dynamic stall model, added mass, flow curvature correction, all this stuff. Suddenly we're shifting a little bit. It's not as great anymore, but we're still doing fairly well. Okay, it's not bad. There's clearly some room for refinement. I'll point out what these things are in a moment. But that is still running on the order of an hour for the whole curve, versus orders of magnitude more. So then we looked at another model. This is sort of another thing that we did off the side. Sandia has a model called Cactus. It stands for, it's something like axial and cross-flow turbine simulation, something like that. Cactus. But all these models have to actually line model and this vortex model. What they have to do is they have to pull in foil coefficients for lift and drag, so you know what's happening at any given point. And we had the hardest time making sense of all this, and we dug back into the literature And we discovered that the data set that everybody was using was actually, there were some things wrong with it. And it was actually it was not very trustworthy. They actually extrapolated, there were very few actual lab experiments, and they extrapolated to other foils and to higher Reynolds numbers, which was highly suspect. So we scratched our heads with this raw. This is all the Sheldal data, which is highly suspect. We found a much older data set by Jacobs, which only had lift but no drag, and that seemed to be well done. So we constructed this Franken data set, and that's what you see with those green squares here. And that actually works reasonably well. So our recommendation was that somebody has to go back in the lab and do these NACA type studies from the 1930s again to get some really good data, especially when it comes to and then we have the issue of static data versus dynamic data, dynamic stalls. So it's a bit complicated. Anyway, that was the final result. This is actually the actual line model embedded in a large eddy simulation. So you don't actually see the blades, you see the effect of the blades. So you see these large dynamic stall vortices shedding here, and then you see evidence of that strong vertical advection and the wake mixing out. And you can tell from how, the size of the smallest eddies, that's still a fairly coarse simulation that runs quite quickly. It should end right there. Good. So there's some open issues. As with any, the old joke is that nobody believes numerical data except for the person that has done the simulation, right? Because there's many things you can tweak. So those are still things that need quite a bit of work. The Gaussian smearing parameter is over what region you implement the actual line model forcing. And then we still have some issues getting the turbulence injection right, and also some debate on how Reynolds number dependent that should be. It should be, but how to implement that. All right, that's the overall result. We did these lab scale tests, and those are the blade resolved 3D simulations. That's the time bar right here. If we can do it with an actual line model with an LES, we have this time bar right here. There's a potential huge savings in additional time. All right, I'm going to switch gears and go mostly to to the family photo album, picture show of what we've been up to in the last few months, actually a few years. This is the satellite image of where we are. We're right here. We have a tidal test site right here, John Sullivan Bridge. We have a new test site here at Memorial Bridge, the Living Bridge project. That's the pier. And then we also have this offshore test site, which we've been using for some wave devices. Gels, where some boats are based as well. And blue dots are where we have commercial marine support, which we've used for different projects. All right. This is how it started. This is back in February of 2009. First deployment of a Gorov helical turbine. This thing right here. This came out of the Tech 797 senior project, actually. This year's another senior project in 2011. And then we use this. This is a 35-foot kit boat, kit pontoon, which Ken Baldwin brought at the time. And then we use that for some DOE projects with a bit more serious instrumentation for some ducted axle turbines. We are up here. That's sort of, we classified our site as a nursery site up to a certain scale. And we said, well, we can then have people go down to Muskegon Channel, which is between Martha's Vineyard and Nantucket Island down here, and test bigger devices. So we brought our platform down there just to try it out. Here we're hanging off of a single point mooring in the middle of Muskegon Channel. In retrospect, it doesn't look all that safe. So the wind, when the wind kicks up in the afternoon, you get this is fully exposed. You get waves in no time at all. We attempted 6 deployments. We were able to manage 3. The rest had to be aborted because of waves and weather. We broke a bunch of stuff. And you can see who was, Matt Rowell is on the platform. He was actually the lead on these experiments. The grad student, Judd, myself, Toby. All right, moving on to a more recent project, the Living Bridge project, which is a smart infrastructure project based at the Memorial Bridge in Portsmouth. The bridge was rebuilt in 2013 under some emergency funding because it was found deficient. It was closed overnight to traffic, and then it took about a year and a half or so to rebuild it. And they used some novel structural elements on the bridge. They're called gussetless truss connections. It's actually rolled and bent steel. They did away with these gusset plates, which are the ones that fail. Look up gusset plates. It's a plate of steel with 1,000 bolts on it, right? That sort of thing. So this is a different bridge, but nobody had actually measured how these operate in the field. They were only models. So Aaron Bell in civil engineering, who's the PI on this project, has instrumented this bridge with dozens of sensors. Another neat thing about this bridge is it's a lift bridge. So every half hour in the summer, you get a lift, and it's sort of a nice impact load of I don't know, 1 million pounds or something. It's like banging the bridge with a giant hammer to get a dynamic response of it. Right? So it's a real it's a great setup for this kind of smart infrastructure type testing. And then we said, well, why don't we, as an added wrinkle and to make it more difficult for us, why don't we try to power everything with tidal energy? And that's where everything under the bridge comes into play. We have a platform there with sensors and whatnot. So living bridge means the bridge is sensing itself. It talks to us via a website and a data acquisition system that reports out to the website via a SCADA system, and it feeds itself with renewable energy. That's sort of the whole living bridge model. All right. It's generally a good idea to try to do tidal energy at estuarine bridges because you can piggyback on the structure that is there. Right? You don't have to build extra structure. You can piggyback on the permitting. And typically bridges are built where the estuary is narrow and the currents are fast. So that's usually, if you're looking for good tidal energy resource, look at bridges. Right? Here are a couple of ADCP measurements, bottom deployed. So location A was Carl Kammerer's deployment, one of the deployments under the National Ocean Survey back in 2007. We did one right here under a senior project to get close to where we're actually deploying at sea. So this is our location right here. And we see it's much more asymmetric. We're getting a much weaker flood tide than ebb tide compared to the more symmetrical mid-channel. And this is about from A to B, cross-channel is about maybe 60 meters. So you move 60 meters across, and it looks very different. And this is it actually overlaid where it's supposed to be. All right. So this is something we got from CCOM and JHC. It's actually it's an overlay of US sonar data on a typical NOAA chart, and you can see that these shallow regions are right here. There's Fort Tree Island, but then this whole shallow region here, which is actually a mooring field for boats. So you can tell from there that on the ebb, it'll actually kind of shift the flow over to the main side. Sorry, on the flood, it'll shift the flow over to the main side, whereas on the ebb, we should be getting the strong flow head on. So we involved Tom and John and their sea bass in the project. You all familiar with this? Basically, instrumented jet ski that will give you it's all in the processing of everything, but Tom can process this to give you some nice transects, which we have right here. So these are transects near the max spring ebb and max spring flood tide, and these are averaged over 42 minutes, I think, going back and forth, multiple passes. Whoops. And over here we have just the surface currents, not the depth, and you can see that on the flood, it's much stronger over here and not strong here. So if we now block out the shipping channel where we can't go, which is between these bridge piers indicated by the vertical dashed lines. When there isn't much left where there is a good resource, clearly the spot right here is the one you want to be in. So that would be on the Portsmouth facing side of pier number 2. Right. So that's where we want to go with the turbine. We designed and built this deployment platform, which consists of 42-inch diameter HDP pontoons, essentially sewer pipe that is welded shut and foam filled. It has a steel superstructure, so we separated the function of providing buoyancy and providing structure. It rides quite loosely on these saddles here. And the whole thing can ride up and down on these vertical guideposts, and we can deploy a turbine through this moon pool rotating in and out. Here's how this rides up and down. And the turbine spins because of the currents in the horizontal direction. Not the up and down, but the currents going horizontally. And then this is how this rotates in and out. It changed a bit. You will see this in a moment. This is a more recent, actually built version of this mechanism. We built a strong back, and we had to actually design some custom bearings ourselves and do this sort of as a one-off. And a winch is used to winch this in and out. Turbine selection, these are 2 vendors we worked with. The first one went bankrupt. Well, not officially bankrupt. They couldn't deliver the turbine. They had no money to finish it up. And we went with the bottom one. This is a 25 kilowatt rotor at currents of 3 meters per second. So we're getting a little bit less than that. But this is essentially this is typically 3.4 meters in diameter. Ours is 3.2 because we had to modify it a bit to fit our system, which was designed for this turbine here originally. Oops. Instrumentation, we have some baseline instruments, cameras, ADCPs, CTDs, and then we have a lot more instruments that we can add as needed. And they're kind of set up in a couple of different systems, a mobile DAC for all the extra instruments, and then the bridge instrumentation and platform instruments that go into a SCADA database. And Kaylin is working on all that right now. We have ADCPs at the bow and stern of this device. Here's some quick data from this. You can see that it actually matters what your sampling time of the ADCP is. Most people deploy ADCPs and then ping, for a short period of time, every 10 minutes or so to preserve battery or to get longer deployment times out of it. And the Tidal Energy Resource Standards actually state these things too, that you should sample every 10 minutes or something. But if you do that, you really smooth out your signal, and you get much stronger currents on like a 5-minute, 2-minute scale or whatnot. And these tidal roses also change as you shorten your sample time. You increase your velocity by, in this case, by easily 20%. And your histogram kind of just shifts out towards higher velocities. I'll skip over that. Deployment timeline, you can see how the project was installed. Guidepost at the pier, the pontoons the first time floating out, and then the turbine assembly. This was in June of this year, and it was being craned onto the platform. Yep, right here, and then it went to the bridge, and here it is operating. There's Kaylin, Lucas, and Ian. Ian designed and built the platform and everything. Kaylin is designed and is working with the instrumentation suite, and Lucas is an undergrad working with her. That's it. It's deployed at the location, and here you can see the turbine operating. It works. Sort of 30-second advertisements that we're doing things in wave and wind as well. This is out at the offshore test site a few years ago. Oops. Yep. This also, and we're about to deploy something there again. This was mostly done by Ken Baldwin with Rob, and Rob is also in charge of the next Healy deployment. And we have a big wind tunnel, so I've been doing a bit of offshore wind studies. So we're trying to simulate this in the wind tunnel, and we can actually do this quite well quantitatively. And here's some other pictures from this. And more recently, we looked at individual wakes, and if you're into similarity solutions and turbulent flows, we actually found that these turbines have an interesting wake behavior, and found some new scalings of those devices. And yeah, this is what most of the first part of the seminar was founded by. This is the Living Bridge funding, 3 projects, which Aaron is the PI, and then this DOE funding as well. That's it. Thank you. All right, it was a bit much, but I hope you get a good overview of everything we're doing in tides. Any comments or questions?
How much are you getting into this? Close to its.
That's a difficult question to answer. At present, it is not, because they haven't provided us with a proper way to rectify the power yet. They have mostly deployed their systems in river flows, where they use a passive rectification system, which is designed for a certain fixed velocity, and that involves a very large capacitor bank. So we discovered in the design of this whole project that the capacitor bank would have to be huge for tidal flows to get a reasonable energy out. So at the moment there's nothing there, so we're getting decent power at certain speeds, but really poor power at other speeds. And we're waiting for them to deliver us an active rectification system, which is the proper way to handle this in tidal flows. But we've run it in off-grid mode so far. We've gotten single-digit kilowatts out of it. The expected output of this device will range from nothing when the tide is not running to maybe 15 to 20 kilowatts peak at the highest speeds. But it's really energy that is important, right? So on average, we'll produce as much energy as for maybe 2 households. So that's sort of a good number to keep in mind. You need a 3-meter diameter turbine. It's 3.2 wide by 1.7 tall to power 2 households. So solar panels are a much better way to go.
So do you envision this technology mostly as real local power for bridges and piers and things, or do you anticipate this as a source for the grid?
The first grid-connected small array has been deployed off of the northern coast of Scotland. I think they have 4 1.5 megawatt turbines installed, axial flow. So they're trying to go grid scale with this. But these cross-flow devices, the way they're operating here, I think that's going to be more niche installations and bridges. You could easily not just have one, but have maybe 10 of those, like on both sides of the pier, up and down. Build them into the bridge pier when you build the bridge, and then you could easily power. The bridge would become a small power put that powers itself and maybe some adjoining things as well. So it can be scaled up pretty easily, but the resource is there's few locations that have enough resource to actually scale this up, right? I mean, you see how much it takes to get 2 households worth. How many of these can you put in our estuary before you're starting to reflect what happens up in Great Bay, right? So we can probably take out, Rob Swift some years ago estimated that the estuary dissipates some 60 to 70 megawatts. So once you take more than a few megawatts out of it, it will definitely affect the dynamics.
After how long is biofouling going to be an issue with performance?
after about a day. Soon, quickly. I mean, we haven't seen much on the blades when the turbine operates. I mean, it does only pull it out, but anything else that's in the water all the time, we do see some tidal fall. It's a big. It's been a big issue on the instruments. We have to clean the AECPs and CTD regularly. Stuff grows in here. So it's biofouling and corrosion. The corrosion is the other thing you find. So we have zinc anodes. The blades are solid aluminum. If you look closely, you will see zinc anodes mounted at the top and bottom. And so we have various strategies on how to deal with that. Yes.
So I've read some articles about low flow tidal power. Could you just quite understand what that's about? Can you just address that relative to this?
So low flow, still doing it like this in stream?
Yeah, are there a different kind of system for extracting tidal power in low flow environments?
Two-part answer. You could go to a simple drag-driven device. This is still a primarily lift-driven device, right? So the blades actually move faster than the flow. You could do something like a cup anemometer, and that can just be pushed by any speed of flow. The problem there is that your energy conversion efficiency is much lower than for these devices. That's first thing. Second is that if you look at how both drag and power scale, drag scales with velocity squared, power with velocity cubed. So if you go into the lower flow regime, the slower flow, and you want to get to the same total power output, you're dealing with twice the drag. That means you have to build a structure that is twice as big or twice as strong. So I think all these low flow ideas will have to deal with significant structural costs. And that's going to be a bit of a non-starter. The only technology that I've seen that seems to get around that a bit is underwater kites. Because you're essentially sweeping a very large area, you're intercepting a very large area of flow, but you don't have to build the structure for that area. So there's a couple of companies that have tried that, and that could work. But then, I mean, I have a hard time avoiding all the lobster traps. So how that would work with dozens of kites flying on the water. Let's see.
Any other questions? Okay.
Yeah. Cameron, walk up. What?
What mechanical design comes with the high torque? How you graph the respect and stuff like that. I was kind of curious, like, what from a design standpoint, how you mitigate against that causing some sort of failure.
Yeah. So if you think about what three-bladed wind turbines, axle turbines. So a three-bladed axial flow turbine in a constant approach flow is a steady-state device, right? You have a certain design angle of attack on the blades, but each of the blades over its span sees the same flow no matter where it is in the rotation, right? So if you then put that horizontal axis wind turbine into an atmospheric boundary layer, things change a bit, right? You have different loading during different parts of the rotation, and that becomes a fatigue issue as well. But for these cross-flow devices, your flow is perpendicular to the axis of rotation, right? In this case, it's from top down. So you end up with, this is what you were asking about, right? So these devices are inherently unsteady devices because as they rotate, look at the yellow vector right here. That's the effective angle, or the relative velocity at its effective angle of attack, right? So your relative velocity sort of oscillates around the leading edge of the blade, and that becomes a fatigue issue. We have looked at how many cycles we get per year. It's high. It's in the tens of millions. So we need to design everything to be below fatigue limits. And if you look at fatigue design curves, that means you have to keep your stresses quite low in these devices. It wouldn't. Well, you could, but it wouldn't really change what you see. I mean, somewhere you have to absorb this, right? So right now we're running with a direct drive generator, a low RPM generator. We could run with the gearbox and a high-speed generator. It doesn't. You still have to absorb this torque somehow in the structure, right? But this is one blade, right? So if you say you have 4 blades that are 90 degrees offset, that means you just take this curve, you plot it 4 times offset by 90 degrees. You add it all together, and you get much smaller spikes here, right? That's basically like the idea. Good question. All right, any other questions? Well, thank you for sticking around. Have a good weekend.